This is the 14th in a series of videos that I'm making to support a elementary number theory class that I'm teaching. And here we're going to build up to and prove Wilson's theorem, and then also look at a couple of applications of Wilson's theorem. So we'll start with the following lemma, and that has to do with square roots of 1 modulo p. So let's see the precise statement here. So we want to start with p as a prime, and then we'll prove that if x squared is congruent to 1 mod p, then x is congruent to plus or minus 1 mod p. So this tells us that working modulo p is pretty similar to working just over the real numbers or over the integers, because obviously if you've got just a plain old integer that squares to 1, that tells you that that integer is plus or minus 1. Okay, so let's maybe see how this proof goes. So let's suppose that we have the hypothesis satisfied. In other words, x squared is congruent to 1 mod p. But then that tells us that x squared minus 1 is congruent to 0 mod p. But that tells us that p divides x squared minus 1. That's the definition of congruence modulo p. But then we've got p divides x minus 1 times x plus 1. That's just by factoring this x squared minus 1. Because notice at this stage we're in the integers, we're not in the integers modulo p, so factorization just goes like normal. But now if p divides a product, then that means p must divide one of the terms from the product. So in other words, we have p divides x minus 1 or p divides x plus 1. But if p divides x minus 1, we see that x is congruent to 1 mod p. And then if p divides x plus 1, then that means x is congruent to minus 1 modulo p. Now, before we jump into the proof of Wilson's theorem, I want to notice that this kind of statement is not true if we're working modulo something other than a prime. So for instance, let's notice that 5 squared is congruent to 1 mod 12, but 5 is not congruent to plus or minus 1 mod 12. So let's talk our way through that. 5 squared is 25. 25 is one more than 24. 24 is a multiple of 12. That shows that 5 squared is congruent to 1 mod 12. But 5 is not congruent to 1, and it's not congruent to 11, which is negative 1 mod 12. Okay, so now let's look at the proof of Wilson's theorem. But before doing that, obviously, let's dive into the statement. And I've written something which is not the standard classical statement, but is a fairly simple extension from the standard theorem. Okay, and so that says p is prime if and only if p minus 1 factorial is congruent to minus 1 mod p. Okay, so notice we've got an if and only if statement here, which means we have two things to prove. Let's prove this reverse direction first. So in other words, we'll suppose that p minus 1 factorial is congruent to minus 1 modulo p. And we hopefully want to end up with p being prime. So how can we do that? Well, let's suppose that we've got a divisor of p. So let's suppose that n divides p with n not equal to p. So if we can show that n equals 1, then we're good to go. So I'll just put that right here as kind of like a blueprint. We want to show that the fact that n divides p implies that n is equal to 1. That's using the definition of a prime to show that indeed p is prime. Okay, so let's see how we can do this. So notice the fact that n is not equal to p, but it divides p, tells us that n comes from a certain set, 1, 2, 3, all the way up to p minus 1. Well, the fact that n divides p means that it's less than p. The fact that it's not equal means that that inequality is strict. But if n is in this set, then it's very clear that n divides p minus 1 factorial. Again, because n is in this set, when we compute p minus 1 factorial, at some point we will have to include n in that product. But now let's next notice that our hypothesis up here, which I'll bring down with this green star, implies that p divides p minus 1 factorial plus 1. Again, that's just the definition of congruence modulo p. Okay, but then the fact that n divides p and p divides this, and we've got some sort of like transitive property of divisibility, tells us that n actually divides this object. So p minus 1 factorial plus 1. But let's see what we've got. We have n divides p minus 1 factorial, and n divides p minus 1 factorial plus 1, but that means it divides the difference in these two numbers. So a long time ago, we proved that if we have n dividing something and n dividing something else, then n divides a linear combination of those. So a difference is maybe one of the simpler versions of a linear combination. So here we've got n divides, like I said, the difference of this with this, but that difference is exactly 1. So we have n divides 1, which tells us that n is equal to 1. But by our previous discussion, that's what we wanted to show in order to prove that p was prime. So that finishes this reverse direction of our proof. Let's get rid of this and then we'll look at the forward direction. Okay, so we just finished proving the reverse direction. Now we're ready to prove the forward direction. And I'm going to leave as a warm-up exercise the first two cases. So in other words, the case when p is equal to 2 and the case when p is equal to 3. That's just a really quick calculation. That shouldn't really take any time at all. But these cases don't really work with the general proof that we're about to provide, so they have to be kind of done on their own. So now let's suppose p is bigger than or equal to bigger than or equal to 5 and a prime number. We want to end up with the fact that p minus 1 factorial is congruent to minus 1 mod p. Okay, so how can we do that? Well, let's consider the following set. And so that set is going to be made up of the numbers 2, 3, 4, all the way up to p minus 2. The fact that we're considering this set, which starts at 2 and ends at p minus 2, is really the reason why this p equals 2 and p equals 3 case has to be considered on their own. And now we're about ready to use our lemma. So let's note that for all values, which I'll call a, from this set, 2, 3 up to p minus 2, we have a squared is not congruent to 1 mod p. Well, how do we know that? Well, let's look at our lemma. Our lemma says the only solutions to x squared congruent to 1 mod p are plus and minus 1. But plus and minus 1 are excluded from this set. That tells us that none of these square to 1. But in other words, these are not their own inverses mod p. So we know that inverses mod p are unique by something that we did earlier involving solving linear congruences. So that tells us that there exists a unique element b from the same set such that we know that a times b is congruent to 1 mod p. And I guess to really point this out, we mean that this b is not equal to a. Because if it were equal to a, then we would really have a squared is congruent to 1 mod p, but we just said that we do not have that. Okay, now we're ready to finish this thing off. So let's start with p minus 1 factorial. And notice that we can rewrite that as 1 times 2 times 3 all the way up to p minus 2 times p minus 1. That's the definition of the factorial. And now we'll use this little argument right here involving elements of this set 2, 3 up to p minus 2 and their unique inverses to regroup all of these numbers with their inverse pairs. So that regrouping will go like this. So 1 times p minus 1, those do not have inverse pairs. Those are their own inverses, and they're the only things with their own inverses, again, by our lemma. And then next, we'll have 2 times 2 inverse. And then after that, we'll have 3 times 3 inverse. And then we'll continue until we run out of numbers. Now, I want to point out that this is a bit sloppy because a priori, we don't know that the inverse of 2 modulo p is not equal to 3. And so here we would be like overcounting a little bit. But just keep that in mind as you're looking at this proof. Really, we're just pairing each of these numbers up here with their inverse. But now those are all going to cancel down just to the number 1, and we're left with 1 times p minus 1. But that means we have this is congruent to p minus 1 mod p, but p minus 1 is negative 1 mod p. And that finishes the proof of Wilson's theorem. Okay, so now we're going to look at some applications of this theorem. Okay, so now let's look at some examples. And these examples are really going to show us how this proof worked a little bit, as well as maybe show us the truth of this statement or give evidence to the truth of this statement. So let's start with 6 factorial, which means we're going to be working modulo 7. So let's notice that we can write that as 1 times 2 times 3 times 4 times 5 times 6. Then, keeping in mind that we want to work mod 7, we can group these in terms of their multiplicative inverses mod 7. So we can write this as 6 and then 2 times 4 and then 3 times 5. Well, notice that 2 times 4, well, that's obviously equal to 8. And then 3 times 5 is obviously equal to 15. Well, 15 is congruent to 1 mod 7 because it's 1 more than 14. 8 is congruent to 1 mod 7 because it's 1 more than 7. So in the end, we're left with 6 modulo 7. But 6 is the same thing as negative 1 mod 7. Okay, so now let's see what happens if we're working modulo not a prime to show that this does not work. Let's look at maybe 9 factorial. So since we're looking at 9 factorial, that means we're working modulo 10. So that means this equality should not hold because we know that 10 is not prime. So let's look at that. We've got 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9. Now, like I said, we're working modulo 10, but there's a bunch of ways that you can multiply numbers in here and achieve a multiple of 10. Notice we can take 2 times 5. That'll leave us with 10 times a bunch of other stuff. What's left over? Well, we've got 3 times 4 times 6 times 7 times 8 times 9. But the important thing is we have a multiple of 10 here, which means when we reduce mod 10, we get that this is 0 mod 10. Okay, so now that we've looked at some of these basic examples, let's look at some applications of Wilson's theorem that will help us prove some nice results. Okay, so our first result that will follow with the aid of Wilson's theorem has to do with taking square roots of minus 1 mod p. And this will come to be known as quadratic residues mod p. So let's look at the statement here. So we want to start with an odd prime p. So that's really any prime other than 2. And then the result says that x squared is congruent to minus 1 mod p has a solution if and only if p is congruent to 1 mod 4. So that means if p is congruent to 3 mod 4, this does not have a solution. In other words, minus 1 does not have a square root. Okay, so we'll start this with the reverse direction. So in other words, we want to suppose that p is congruent to 1 modulo 4. Okay, well, what does that mean? Well, by the definition of congruence mod 4, that means that 4 divides p minus 1. Okay, but if 4 divides p minus 1, that tells us that p minus 1 over 2 is even. Well, let's talk our way through that really quick. The fact that 4 divides p minus 1 means that p minus 1 divided by 4 is an integer. Well, we can write 4 as 2 times 2, move one of those 2's up, and then that means p minus 1 over 2 has to be an even integer. Okay, great. So now we want to look at Wilson's theorem. So Wilson's theorem tells us the following. First of all, that p minus 1 factorial should be congruent to minus 1 mod p. But we're going to take this p minus 1 factorial and write it like in a fancy way so that we in fact construct this square root of minus 1. So let's write it like this. This is going to be congruent to 1 times 2 times 3, ending at p minus 1 over 2. Okay, so why did we need p minus 1 over 2 to be even? Well, that's because we wanted an even number of things in this product for what we're getting at. Okay, and then let's write the rest of the terms. So that'll be p minus 1 over 2 plus 1 times p minus 1 over 2 plus 2, ending at p minus 1. Okay, great. So let's notice that in this product, there are p minus 1 over 2 terms. That's pretty obvious because we're just counting them 1, 2, 3 up to p minus 1 over 2. And then in this product, there are also p minus 1 over 2 terms. That's a little bit trickier to count, but still pretty straightforward. Okay, so next I want to notice that each of these is exactly the negative value of one of these. So this guy right here is actually minus p minus 1 over 2. Now, how can you see that? Well, if you take p and subtract this guy right here, you'll end up with this guy right here. So I'll let you do that calculation, but that's not too hard to see. And then the last one of these terms is equal to minus 1. Okay, so now let's rewrite this a little bit. That means we have this is equal to 1 times 2 times 3, all the way up to p minus 1 halves. And then reordering this, we have minus 1 times minus 2 times minus 3, all the way up to minus p minus 1 halves. Like that. Okay. But what can we do from here? Well, we can use the fact that this is even and take out a factor of minus 1 from each of those. So if we take out a factor of minus 1 from each of those, we have minus 1 to an even number. But clearly minus 1 to an even number is plus 1. But then after we do that, we've got a copy of each of these multiplying each other. We can put those together and we'll see that we have, this is congruent to 1 times 2 times 3, all the way up to p minus 1 over 2 squared. So we haven't used Wilson's theorem yet. We've just like set up the left-hand side of Wilson's theorem and then done this like crazy calculation. But Wilson's theorem says that this object right here is congruent to minus 1 mod p, but that means this thing that we ended up with is congruent to minus 1 mod p. So in fact, after all of this work, we've constructed our solution to this congruence. X squared is congruent to minus 1 mod p, and this is our value of x. This product of 1, 2, 3 up to p minus 1 over 2. Okay, so we finished this direction. So now let's look at the other implication. So we finished the reverse direction. Now we're ready for the forward direction. So let's suppose that x squared congruent to minus 1 mod p has a solution. So which solution? Well, we'll just call that solution x just to say that maybe this congruence is true right here. So just to reiterate, x is a solution to our congruence. Okay, and now we want to work by way of contradiction. So by way of contradiction, suppose that P is not congruent to 1 mod 4. So P not being congruent to 1 mod 4, together with P being an odd prime, means that P is congruent to 3 modulo 4. But now we can look at a similar object to what we did in the other direction of the proof, and that is P minus 1 over 2. So notice that that is going to be equal to P minus 3 over 2 plus 1. So notice P minus 3 over 2 is even. So I'll put this like in a purple box and then just say that this is even. How do we know that's even? Well, we know that's even from this congruence here using an argument which is parallel to what we saw in the proof of the previous direction. But we've got purple box, which is even, plus 1, which means this entire thing must be odd. So in other words, P minus 1 over 2 is odd. Okay, so now let's take our number x and raise it to something involving P minus 1 over 2. Okay, so first off, we know that x to the P minus 1 is congruent to 1 modulo P, and that's by Fermat's little theorem. Well, that only holds if P does not divide x. But since x is a solution to this equation right here, it's kind of obvious that P does not divide x. Okay, so that's one fact. Now we can introduce this P minus 1 over 2 into the situation. We can do that by taking x to the P minus 1 and rewriting it as x to the square, x squared to the P minus 1 over 2. But by our original assumption, x squared is congruent to minus 1 mod P. So we've got that this is congruent to minus 1 to the P minus 1 over 2 mod P. But now we've got a problem, huh? Because now that tells us that we've got this is all congruent to minus 1 mod P. Why is that? Because we've got minus 1 to an odd number, which clearly gives us minus 1. So this is congruent to minus 1 mod P. But what do we have? We've got x to the P minus 1 is simultaneously congruent to 1 and minus 1 mod P. But that tells us that 1 is congruent to minus 1 mod P, which I think we're pretty much done with this, and that says that that's impossible if we're dealing with odd primes. But just to really put it into perspective, by the definition of congruence mod P, that means P divides 2. But again, no odd primes divide 2. That's pretty obvious. So that leads us to our contradiction. So what did we contradict? Well, we contradicted this supposition right here that P is not congruent to 1 mod 4. So that means P must be congruent to 1 mod 4. And that finishes the proof of this theorem. Now we're going to look at a nice corollary to this theorem that is related to some other theorems that we've seen in the past. Okay, so our corollary to this theorem is as follows. There are infinitely many primes that are congruent to 1 mod 4. So in other words, infinitely many primes of the form 4k plus 1. So being of the form 4k plus 1 and being congruent to 1 mod 4, that's the same. So I want to recall in a video, we proved that there were flat out infinitely many primes. We did that a couple of ways. And then if you're in the course that I'm teaching, as part of a group work assignment, you proved that there were infinitely many primes congruent to 3 mod 4. In other words, of the form 4k plus 3. And I alluded to the fact that other theorems like this existed, but were a little bit trickier to prove. Well, now we've got one of the tools necessary to prove this theorem. Okay, so let's see how this goes. Well, we're going to start off just like the proofs of our other infinite prime theorems, and that is by way of contradiction, suppose we only have finitely many. So by way of contradiction, let's suppose that P1 up to Pn are all of the primes that are congruent to 1 mod 4. So in other words, there are only finitely many, and we've got a list of them. Now we're going to want to construct a number that will really cause a problem with the finiteness of this list. And then, well, since we want to use this, we better use this along the way. So what number do we want to construct? Well, it's as follows. So I'll call it capital N again, and it will be equal to 4 times the product P1 to Pn squared, and then plus 1. So let's point out that this is congruent to 1 mod 4, just like all of our primes. Okay, so next, let's suppose that we've got a prime that divides this. So let's suppose P divides N. Well, what does that tell us? That tells us that N is congruent to 0 modulo P. Well, that's like one of the definitions of congruence. Well, how do we know there's a prime that divides it in the first place? Well, that follows from the fundamental theorem of arithmetic. Okay, so now let's take this and rewrite it a little bit. Let's notice that this tells us that 2 times P1 all the way up to Pn squared is congruent to -1 mod P. So we got that just from inserting this definition of N into this congruence and moving the 1 over and then moving the 4 inside of the perfect square. Okay, but let's look at what we've got. We've got a solution 2 times P1 up to Pn of the equation x squared is congruent to -1 mod P, right? So our x is this product right here. What does that tell us? That tells us that our prime is congruent to 1 mod 4 by this theorem. So let's point that out. So this tells us that P is congruent to 1 mod 4, but in turn, that tells us that P is equal to Pi for some I between 1 and n, because our assumption was that this was all of the primes. Okay, but let's see what we've got. We've got that Pi divides n. That's just rewriting this with Pi. But Pi also divides this 4 times P1 up to Pn squared. Well, that's obvious because Pi is one of the terms in this product. But now Pi divides this difference. Well, what's the difference? The difference is exactly 1. So we have Pi divides 1, but that tells us that Pi is equal to 1, but 1 is not a prime number. So that leads us to our contradiction. And so again, what did we contradict? We contradicted this assumption that there were finitely many primes of the form 1 mod 4. So indeed, there are infinitely many such primes. Okay, so now let's get some warm-up problems on the board so that you can practice using Wilson's theorem. Okay, here are 2 quick warm-up problems based on Wilson's theorem. The first involves verifying Wilson's theorem and really diving into the proof of Wilson's theorem via this example. So the first is to look at 16 factorial mod 17. So that should clearly be congruent to -1 mod 17. But what I want you to do is write this in terms of inverse pairs to really exercise your mind to understand that proof of Wilson's theorem well. And again, let's look at maybe 14 factorial mod 15 for the non-prime case. Then finally, we've got this kind of variant of Wilson's theorem, which is nice to prove as well. And that is show that 2 times P minus 3 factorial is congruent to -1 mod P. And that's a good place to stop.